how do people feel about the pace of the class so far? Is it like still manageable? Okay, right. Like if someone feel that like I'm going too fast, you can let me know, or you can email me or something. Right? Okay. But yeah, like I kind of excited to tell you a lot about many advanced things. So that's why the pace of the class might be not as easygoing as in like a more basic one. But yeah. All right. So what we're gonna do today is again like a continue to see more advanced example of dynamic programming. Again, like I think whenever you see a problem and you wanna think like, okay, let's try to use dynamic programming. The first thing you need to do is like, okay, try to get recursive formulation of the problem. Once you have that, look at that formulation and see if that formulation has small number of subproblems that you ever need to look at. If that's the case, then dynamic programming is gonna work. How? Just create a table and fill in the table bottom up using your recursive formulation. Okay. So last time we see like kind of several examples, and today we're gonna see more. But like what happened in like previous class is that most of these example, when I said at the table, like we try to come up with recursive formulation and create a table. The table really look like a table. It's like a one-dimensional table or 2D table. And today you're gonna see like two example when the table doesn't really look like a table. Like it's not like a just two-dimensional table. It can be something else. So let's see now. Okay. So we come back to maximum independent set problem, right? So this is again is an NP-hard problem. Just to recall what is this problem. You have a graph here, and let's say now you have the weight WV for each node V, okay? Some weight here, right? And we want to find independent set like this. So this shouldn't have any edge between them. That's why it's independent, right? It's a set that is there is no edge between any two vertices in a set. And we want to find independent set that is maximum. So in this case, it's maximum in the total number of weights, not just maximum size. Okay. And we know that this is an NP-hard problem. And we see how to get something non-trivial, like something faster than 2 to the n time in like a 2 class ago, if you remember, like something like 1.6 to the n. And in your homework, you need to improve upon that. Yeah, right. Okay, so that's not too fast. Like it's like faster than trivial, but it's still exponential. But now, one thing that I want you to take from this class is that, okay, whenever you have an NP-hard problem, and let's say it's an NP-hard problem on graph, but whenever your graph is a tree, then you can actually solve it. You usually can solve it in linear or polynomial time. Any NP-hard problem on a tree usually is easy. Okay, and we're gonna see how to solve this NP-hard problem on a tree today using dynamic programming. Okay, so in particular, the input is a tree. Okay, and each vertex has a weight WV. Vertex V has the weight WV. Okay, and we want to find independent set with maximum total weight. So, like for example, this is example of independent set with maximum weight here. Okay, so that's the problem. Any question about the problem statement? Okay. So Now suppose that I tell you that, okay, let's try to solve this problem using dynamic programming. Okay, so the first step is, okay, let's try to get some recursive strategy. Anyone have a suggestion? How would you get a recursive strategy?
Can I just ask a question about like a non-recursive strategy? Couldn't you just take the maximum of like basically you're either taking even or odd depths, and like you just take the maximum of like how many nodes are at even or odd depths? Is that
that is like some good heuristic, but it might not be the best way. Let's see if there is an example. Like, let's see. Let's say this is like 100. This is 100, and this is 1 and 1. Right. Okay. So you would need to pick these two guys. Okay. Yeah.
For the recursive, we could either include, we start at the root,
Okay.
and we either include the root and then go 2 levels down and recurse on those 4 subtrees, or we don't include the root and recurse on the 2 subtrees that are directly below them.
Very good, very good. What's your name?
John.
John. Thanks, John. So what John just said is that, okay, let's try to do something like let's try to get a recursive strategy. And the idea is just that if you just, let's say, focus on the root node, actually on any node, but it's easier to just focus on the root so that we can get easy recursion. So let's look at the root, right? And there are just 2 choices for the root, whether you want to include it into your set or not. And let's start with, suppose that you don't include it, you reject it from your solution. Then, okay, you get you get some tree that you deleted the root node. And you can ask yourself what are the subproblems that remains. Basically, the subproblem that remains is just the subproblem of rooted at each student of the root. It's the same problem. Just look at the subproblem of each child of the root. Okay. Now, what if you accept? Then your solution would be, okay, this should be W of R. Okay. If you know that you're going to accept the root, then you put the weight of the root there. And now you're going to recurse on another tree. What this tree star should be? It should be a tree such that you remove the root together with all of its children. Because all of its children cannot be in your solution anyway. Okay. So that's the recursive strategy we have. Again, if you reject, you recurse on each of the subtree here of each child, right? And then sum them up, just sum the best solution of each subtree. If you accept, then you put this to your solution, and now you recurse on each of these subtree of the grandchildren and sum the best solution of the grandchildren. Okay. So okay, we have the recursive strategy. So now, how many subproblems are there that we're gonna need to look at ever?
It's how many children the root has, or sometimes the grandchildren, which can be as much as the amount of nodes in the graph.
Well, so when you look at the grandchildren, in this case, there can be can be not too many, but okay. But you might not need, when you recurse, you need to look at the subproblem that might be a children of grandchildren and grandchildren of grandchildren and so on, right? So it's not just that we look at the subproblem that we look at is just the grandchildren or the children. When we recurse further, you go down further. So again, how many subproblem would there be ever that we look at? If there are like n nodes, how many?
And subproblems like the tree rooted at each node.
Exactly. Yeah. It's n because the type of problem that we can look at is just take some node and then look at the best tree rooted at that node. That's how you that's how you recurse. Like if this is a tree star, T star, we look at the best solution of T star, and this is the case for each node. Okay. So now you have you have a recursion. You bound the number of subproblem that you ever look at. So now I just need to fill in the table. Now, okay, what should the table look like? So if I have an array, memo, what should the index of this array depends on?
You just make it like the in-order traversal of the tree, and then have each node have its own like max weight independent set value.
Right.
Indice in the memo.
Good. Yeah. Like basically just you have like a memo for each node. Yeah. So now you can just write down the pseudocode. Okay. You have a tree that said that the root is R, and create a memo which is an array. Just create a memo for each node V, like a cell for each node V, which store the best solution rooted at V.
Could the memo also be pointers instead of like just a one-dimensional array?
Yeah, it could be a pointer. Yeah, it's just that like this guy you associate this guy with a node V. Yeah. Okay. So you have this table, and now just try to fill in the table bottom up. So what does it mean to fill in the table bottom up here? Well, when you recurse from the root, you need to know the solution of your child. So if you want to fill in the table bottom up, you need to start from the leaf. Right? So just start from the leaf and go up. And for each cell, then what we need to do is just compute, just fill in each cell in the table using our recurrent, and that's it. So, and suppose that our tree has at most B children, like every node, suppose it has at most B children. What's the running time of this algorithm?
O of n times b squared.
O of n times b squared. Why is that?
Because the worst case scenario is each child has b children, so you do b times b to get the total number of grandchildren, and you'll just do it for per each node.
Exactly. There are n nodes, and to compute this, you spend b time. To compute this one, you might need to spend b squared time. So that's n times b squared. Okay, good. So that's polynomial time. And one exercise is that actually, if you look at the same algorithm but just smarter analysis, you can get it down to just ON. And the trick is just try to prove this one. When you sum the number of grandchildren throughout the whole tree, this is still ON. So the total time, for some node, you might need to spend b squared time, but the total time that you spend on overall node is still ON. Exercise, you can try to do this. So the same algorithm works in actually linear time. Good. So this is one example of when you do dynamic programming, but the table kind of look like a tree. Okay. All right, so let's go to the next example when table looks different. Here. Okay. Oh. All right. Okay. We're gonna try to solve, like, look at traveling salesman problem. And okay, we have seen some dynamic programming table that looks like a table, or like it's indexed by a vertex on the tree. Again, like I want to mention again that, like, for many problem on the tree, like many times you can do some greedy, but most of the time, whatever problem it is, there is always an ultimate solution on the tree, and you can usually just solve it by dynamic programming. Like whatever problem there is, usually you can solve it on a tree in some polynomial time or linear time using DP. Okay. Now let's look at like more like advanced example when the table looks even more complicated. And okay, the problem is traveling salesman. So in this problem, you have a graph G, right? And there are like a node start from 0, 1, 2, up to n. Okay. And between every node, you have an edge. An edge has the distance or the weight of okay, like if it's weight from node I to node J, then there is a weight of this, Dij. Okay. And what we want is to find a cycle that visit every node once exactly. We want to find a shortest cycle that visit every vertex once. This is also called Hamiltonian cycle. So let's see one example. Example is this graph, right? So there is an edge between every node, and you need to find a cycle that visits everyone once, and this cycle should be shortest. So the way to do for this graph is like to go in this way, because if you use this edge, it's too big. Okay. That's a problem. It's like one of the most famous NP hard problem. Okay, so it's NP hard. So again, we don't hope for polynomial time algorithm again, but can we solve it? Can we solve this problem at all in finite time? Anyone have some brute force solution in mind?
Try every permutation of like the order that you visit them. Check if it's valid. I guess it would be valid if you always put it one at the end. But just check the cost and choose the minimum.
Exactly. So just try all permutation of n vertices or n plus 1 vertices and check the cost, which one is the minimum. Right. What's the running time there?
If there are n nodes and factorial.
Yeah. So the running time, yeah.
Factorial times n, because you need to check each time also.
Right.
Yeah.
So the running time for brute force solution is something like n factorial times n. And n factorial is around like this thing. So the way I think about it is like n factorial is n to the order of n. Yeah, that's how I think about it. So this is basically something like n to the order of n. So not that great. Okay. And okay, what we're gonna do today is try to get something like 2 to the n. So that's like better, significantly better if n is big. Okay. So now, suppose that okay, this is our goal. We want to get improvement to 2 to the n. And let's say also that, okay, let's try to solve this using dynamic programming. Okay. So we need to like start with some idea how to get a recursion, right? And the recursion should be such that like the number of subproblems that we look at is something like 2 to the n. Many subproblems that we gonna look at in the recursion at all. Okay. So if that is our goal, it kind of restrict ourselves to like to come up with some solution already. Like this is a goal, this running time, and we use DP, dynamic programming, so that should be the number of subproblems. So with this in mind, like what would be your guess on like each subproblem? What should it correspond to?
Because it's 2 to the n, maybe we're making binary trees. Like if we're making a lot of trees out of this graph, each node would have 2 children.
Mm-hmm. And how why does binary tree has something to do with 2 to the n?
I don't know. It's kind of just intuitive because I don't know. It's hard to
Okay.
explain, but
That's interesting, but yeah. Any other ideas?
Does the subproblem correspond to including or not including each node, or each edge would it be? I'm not sure.
Okay. Yeah, like if for each node that might be like that looks more close to the correct answer because there are n nodes. If you ask how many subset of vertices are there, then that's 2 to the n many subset. For the edge, there are like n square, n choose 2 edges. So the like a number of subset of edges that's 2 to the n choose 2. Okay. So okay, it's not clear but like for me like I would guess that okay if I try to get some like if this is my goal, then let's try to like make it such that the number of each subproblem correspond to some subset of vertices. That's the number of like 2 to the n is the number of subset of vertices in the graph. Okay. Just some hint basically. Okay. But at first, the first step, right? Okay, how would we get recursive algorithm or some strategy at all? And that's not so clear, actually. Like from this problem, you kind of want a cycle, and like if you have a tree problem, you kind of start with a root and like ask what can you do with the root. If you have a sequence, like a sequence problem, you can ask like what do you do with like the last guy. That's like, and you have a choice on the last guy, and you ask okay if you do accept the last or reject the last, then what you get as a subproblem. Here is not so clear at all. Okay, and so like the point is that like for some problem it's not really clear how to get recursion. And here is like the really like ingenious step, like a creative step that we're gonna do. Okay, we're gonna try to adjust or reformulate the problem a bit so that now it becomes more amenable to recursion. So, okay. we're gonna try to reformulate the problem because when we want to find the best cycle, right, it's not so clear how to come up with recursive strategy. Okay, so let me try to formulate a new problem. It's like this. Okay. So in this problem, like I'm giving like a set of nodes and some number k like indicate like the last vertex. So what is this? This denotes the shortest path that I'm gonna start from 0. I fix that I'm gonna start from 0, and then I'm gonna visit everyone here in some order, and then I'm gonna end at k. Is this clear what this is? Okay. So now my question is, suppose that you can, like, by the way, like this looks like something that easier to get recursion because it's a path. So there is like an ending point, there is a starting point. Okay. But if you can solve this problem, suppose that you can compute all of this, like for all k, ranging from like you get like you know this like for k when k equals 1 and k is equals 2 and 3 and so on up to n. If you know all these n numbers, can you tell me what would be the solution for Hamiltonian cycle? So I give you 1 minute to think about it.
Just try all of them. Like this.
Can you write down like what is the best cycle here in term of this guy?
I have a question.
Yeah.
What is 0 not a part of like the graph that we're looking at?
Oh, it is part of the graph. It's just that like I just said that I'm gonna start from 0
Okay.
anyway, and then I'm gonna visit everyone here.
Okay.
Yeah.
So it's just gonna be like the minimum of like path to k, like for all k, it's the minimum of path to k plus the distance to get back to 0 to finish the cycle.
Yeah, from k to 0.
Yeah.
Yeah. Yeah. Good. Yeah.
Yeah, would you actually need to choose not only k, but maybe something called j, like from 0 to j and then k to 0, like entering the 1 to n and leaving the 1 to n?
Okay.
It's already in the path, right?
It says starts from 0, but it's a separate 1 to n. Is that true?
I don't quite get what you suggest actually.
Okay, we say we start from 0.
Yeah.
But our path only considers 1 to n, it excludes 0.
Like it
So-
start from 0 and then we sit 1 to n.
Yeah. So we test every entry into the 1 to n connection from 0, and we also test every exit from the 1 to n back to 0. Is that true?
It's not quite what I have in mind, and I don't think that is correct. But what's your name again?
Scott?
Scott. Okay. What Scott? What you just suggest is actually correct. So let me repeat what Scott just said and explain. Right. So what is this thing? Let's try to draw it. It's like if this is 1 to n, right? It asks for a path that starts from 0 and then somehow end at k, right? And visit everyone and then end at k. And if I take another step by going back from k to 0, that's gonna be a Hamiltonian cycle. Some Hamiltonian cycle. But I know that like the best Hamiltonian cycle will have the form that you can just start from 0 because it's a cycle, and then it's gonna end at some node k, but we don't know which k, and then go back from k to 0. So all we need to do is just take the minimum over all k, there are n choice, and which is like we take this one plus the distance from k to 0. Okay, just this is an answer. Take over all choice of k, right? And then you try to visit everyone and end at k, and then go back from k to 0. And that's like if you can. So it means that if you can compute this thing for every k, then you're good. Then you can compute the best Hamiltonian cycle. Okay. So now, with this in mind, we're gonna try to come up with the recursion for this guy. Okay. So now, like we try to get a DP algorithm for path, not cycle. Okay. So I give you some time to think about this, right? So suppose that, okay, let's write down S to be some set, like in this case, let's say 1 to n. And if you want to compute this guy, right, in the recursive way, how do you do it? This is just the definition of path S and K, right? How can you compute this guy based on maybe like some smaller set?
Sorry, I have a question about the recursive relation that you explained. So for every single node, there's an incoming edge and an outgoing edge. And it seems like we're taking like minimum over all possible incoming edges to 0. Why don't we care about which is the outgoing edge? Like why are we always assuming there's an edge from 0 to 1?
Good. Let's say that like I didn't say this, but good question. Like every edge here has weight I and j, and they are symmetric. So they have the same weight. So it doesn't matter if you go from 0 to k or k to 0. It has the same weight.
Yeah, I'm saying, but there's 2 of these edges. So are we always taking the edge from 0 to 1? They're numbering like if you scroll down to.
Oh.
Sorry,
Here.
maybe I'm misunderstanding.
Here it might go to 3, it might go to 4 and 5 and then 10 and so on. Like this one is it just need to start from 0.
Oh, sorry. Yeah. Okay.
And then visit anyone in this set once. Okay. Yeah.
Sorry, just clarifying question because I don't think it was specified. For the TSP, it has to be a fully connected graph, right?
It's fully connected graph. Yeah. More question? All right. So good. So maybe I give you like 2 minutes in class to think about how would you come up with a recursion for this guy. Yeah.
Would it be the min of all paths of S excluding K that
Is this what you suggest solution right now?
yeah.
Let me like I give you like 2 minutes and then everyone can try to think about this. Yeah. Okay. Okay. Any suggestion?
This might be wrong, but there's, I guess because it starts from 0, n minus 2 vertices that could be like the second to last one. So you could recursively take the shortest path from 0 to each one of the second minus, or the second
The
to
second
multiple
last.
second to last. And then add the distance between that one and k, and then find the minimum of all those.
Good, good. Yeah, very nice. So your name is Guy.
Yeah.
Yeah, good. Yeah. So what Guy just suggests is that, okay, this is a solution that you start from 0, visit everyone in S, and end at K. So we want a recursive solution that like maybe S, like the size of the set S is smaller. So what do we have? What choice? Like how do we come up with this? So the idea is that, okay, if you need to end at K, to go to K, you must come from somewhere. And there are like not too many choice to come from K. Like just someone from S need to go to K. So all you need to do is like just guess what is the second last guy. The last guy you know, so you guess what is the second last guy. What is the best second last guy? Right. So this is a formula, but let me draw something. You have 0, you have S, and you know that you need to end at K, right? So let's say that this is the set S minus K, right? So the solution should look like it start from 0, visit everyone here, and go to K. You don't know which guy is this, but like it must be some guy X. So what you can do is just you take the best guy X, visit everyone, and end at X. So this is I draw this thing. This is this part, right? And then you just go from X to K. So now this is a good recursion because like the size of the set here is smaller. Like it's smaller than S. Yeah. Any question about this recursion? Yeah.
Because you mentioned earlier, like the distance is the same whichever way you go. This is the exact same thing, like symmetrically, as like choosing the first node to go to instead of the second to last node, taking min over those, right?
It's you still fixed to start at 0.
Yeah.
Yeah, but yeah, like now you just say that you need to end at K, and like to come to K you need to come from somewhere. Yeah.
Could you also just start at 0 and then choose a node like that?
Yeah, that's
Oh, I see what you mean.
yeah.
I see what you mean. Thanks.
Yeah.
Sorry. Yeah. So you can say that, okay, like define a problem where like maybe you have like a parameter 0 here too.
But you would just change S the exact same way. You would just like take out node 0, right? And like starting from
But here S,
wherever.
like right now S doesn't contain 0. Like I define the problem
Yeah.
so that S doesn't contain 0.
Right.
But I think I get your idea. It's the idea is gonna work. Yeah, it's just some formulation. Yeah. So, yeah, like what's your name again?
It's Ellen.
Ellen.
Yeah.
Yeah. So what Ellen suggests is, okay, instead of guessing the second last guy, you can also guess like what's the second guy after 0, for example. Yeah. Just if you do that, it's gonna work. Just need to like define the function in the correct way so that it captures that idea. Good. So now that's a recursion. And you can ask, okay, we get a recurrence. How many subproblems we're going to look at here? Any quick answer?
I mean, I think it's 2 to the n, no? Because it's subsets.
Yeah, it's almost 2 to the n, but not quite.
Maybe to the n times n, because not only is the state set, but also the node you end at within the set.
Good. Yeah, it's 2 to the n times n. Correct. What's your name?
Maxim?
Maxim.
Yeah.
Okay, cool.
Just call him
Thanks.
Max.
Max. Okay. Yeah. All right. So basically, when you want to count how many subproblems are there, usually just look at your recurrence, right? And look at how many possible each of the index can there be. This is a set. There are 2 to the n many possible sets, and this is just one node. There are n many possible nodes, so that's 2 to the n times n. So that's like the possible number of cells that you need to fill in this weird table. Okay. So you can see that the table now looks like the index can depends on a set, not just like a 2D table, but this is like a can think like this is a set of the table of size 2 to the n by n too. Yeah. Right. Okay. Good. And with this, like if the number of subproblems is something like this, then you can hope to get like a DP algorithm with this kind of running time. Okay. And now just try to, yep.
I just had a question about the notation that you use. So when you're the recursion, when you're doing like the minimum path to get to each x, you're looking at like a subproblem where you're taking out k and x, correct?
Yeah.
So why is k in brackets and x isn't in brackets? Like, is there a difference between k and, like they're both just 2 points that we're taking out?
Oh, here I remove k because k is not in this blue set anymore.
Okay.
And x, I don't take x out of s because x is in s.
Oh, x is like the new k.
X is like a new k. Yeah. All right. More questions?
We figure out what's the
Okay. So now like just need like now it's kind of easy. Like we kind of see more and more example, and like okay you know the recurrent, you know the subproblem. Like number of subproblems usually just determine the running time, and just try to fill in the table.
I mean, there's 2.
So you start with like a table that indexed by the set and a node k. Now just fill in the best case. The best case is maybe the set of size 1. Like when s is of size 1, this is just the cost to start from 0 and go to k. So the cost here is just from 0 to k. And try to fill in the whole table. So need to loop throughout the table in the correct order. What's the correct order here? We need to like fill in the table when when s is ordered by is in increasing order by the size of the set. As long as we do that, then it's good. Because whenever you look at like the recurrent is just such that when you want this for s, you're gonna look up for the cell that depends on the set of smaller size. So as long as you loop through, like the order of loop is increasing by the size of s, that's good. Okay, and you just fill in this table using the recurrence we have, and at the end we know this guy, and the min cycle, the minimum Hamiltonian cycle is just what we discussed here from the beginning. Okay. Good. Right, so that's the running time. The running time is like, this is like, and we need to look for each k too. For each k, okay. So the loop, the number of round in the loop is like 2 to the n times n. That's like the number of subproblems. And for each subproblem, you take n time because you kind of take mean over n numbers. So that's the running time. Okay. Question about this algorithm? Okay. So this is the state of the art, right? And people like traveling salesman is such a like classical problem, one of the first NP hard problem, and people try hard to improve upon 2 to the n. No one knows how to do this yet. It's like a really nice open problem, but like 5 years ago, like people can improve this by this kind of running time. And it works on special graph when the graph is bipartite, and if you assume that matrix multiplication, you can multiply matrix like really fast. So yeah. So like it's pretty open basically. Yeah. Okay. Sorry, 1 second. Okay. Okay. We're gonna look at another example. Okay. So everyone learned about binary search tree before, I guess, right? And we learned that, okay, any binary search tree, you can make it balanced. If there are n nodes, you can make it balanced and the depth is log n. And that's optimal in the worst case, right? Because you cannot make the depth of the tree to be less than log n. Okay, that's good, but suppose that we know something more. Suppose I have more information, right? That, okay, I still have like n many keys like before, but suppose I know the probability that each key gonna be like will be accessed. Like some key will be accessed more often. Let's say I know that the first key will be accessed with probably 99%, and maybe the rest is like of equal probability. Suppose I know this, like we can ask, like, is it the case that like balanced binary search tree is still optimal with this info? No, right? What should you do in this case?
You should just put the biggest one at the top and then the smallest one here and then everything else.
Yeah. Like if you know that the first guy will be accessed so much often, then just put it on the top, so that like the cost of access it is like just 1, and the rest maybe make it balanced or make it nice according to the probability of them. Okay. So that's the question. Like and the question basically that I want to ask today is like, okay, suppose that someone tell you this information, right? How can you design the best binary search tree according to this information? Yeah.
Could you look at this problem as like trying to minimize the expected runtime?
Exactly. Yeah, we want to minimize the expected search time. And that's exactly what I'm gonna go to. If I denote like the search time, like so you know that the search time of key k, if you fix the tree to be t, like if the tree is like this, and the kj and j is here, then the search time of key j you need to spend needs to start from here and then go here, so it's 2. Like so the search time for any key is like the depth of this key, and so I use this to denote the depth of key j. And so you can ask like what is the expected search time when you know this probability, and it's gonna be just this one, right? Like you're gonna search key j with probability k, and you're gonna pay depth of key j. So that's the expected search time. So the question is basically then like, suppose that we know pj, how can we find the tree that minimizes this expression? Okay. And just some example, like here I have an example where I'm gonna access 1 with really high probability, access 2 with like a lower probability, and 3 and 4 is like access with even less probability. So this is like just the tree that looks balanced, but and you can compute the expected search time. It's like a like what for key 3 you spend just 1 because that's the depth of 3, and you like that's the probability of 3, and for these 2 keys you pay 2, for this first key you pay 3, and you multiply with its probability and you get some number. Okay. And I do the same for this one, and you see that okay, this looks balanced, this is not balanced at all, but for this probability distribution this one is better. Okay, so that's the problem. Like we give we are given this information, you get this pj for all j, and you need to decide optimal binary search tree that minimize the expected search time. Okay. So this looks like a non-trivial problem, okay? And is it solvable at all? Like, what would be like some brute force algorithm? So the brute force algorithm would be just let's try all binary search tree and compute each like an expected search time for each of them. So that would work, right? But like the running time would be bad, because there are something like 4 to the n many binary search tree out there. Not exactly this. It's actually like the Catalan number, and you can look up what it is. It is like a number that characterizes the number of binary search tree, but also like it counts 20 different objects that looks very different, but they are actually the same thing. Like it counts the same thing. Okay. So this is again nice number to look up in Wikipedia. You might have fun, but okay. How can we get a better algorithm? Okay. So let's use DP again. And yeah. So tell me what is a recursive strategy?
I guess.
Alan?
Yeah, I have an idea that's not great, I think. Let's start with a node. If the probability of searching for one of its children is higher, you can rotate. But then the thing is you have to recurse on that node itself if, again, the probability of searching for one of its children is higher.
Like you said, let's try like the root, and if like the children have higher probability, let's rotate and try
Then you
again.
have to like do it again on
Yeah.
the same node.
It's not so clear how many rotations you need.
So for we try to root the tree at every node, and we split it into two halves, the keys that are less than R, kind of just on there, and the keys that are greater than R, and then we get their solution too, and then they break it down also.
Very good. Thanks, Maxim. So what you said is like, okay, the root must be somewhere. Like one of this n node, one of them must be the root. And once you fix the root, you're gonna like kind of basically separate the problem into two sides, the one that is less than R and the one that is greater than R. And you're gonna try to kind of get the best tree inside each of these. And then like compute the cost of the whole tree when the R is a root. And try the best R. Okay.
So for doing this, I assume you have to reweight the probabilities. So like let's say R was, 0.3 probability, then for all of the keys greater than R, you basically divide their or you like re-sum up their probabilities and like reweight them. Is
That is like good. Like you might need to do that, but at the end you will see that once we like at the end of the day you don't need to do it actually. Yeah. And the reason is maybe like things just cancel out like when you reweight the probability to be with respect to this whole thing, and like it's gonna cancel out in this formula and yeah. But okay. So but okay. Yeah, I just described what Max just said about the recursive strategy. Any question about that?
Would we always choose R to be the node with the highest probability?
Not clear. That is the best way. Why is that? Well, I cannot come up with like a counterexample right away, but it could be that like you kind of need to choose R to be need to sacrifice R somehow, such that like the best tree actually like so that you can get the best tree below somehow. Yeah.
just like for a counterexample, think of like, let's say you have 0.8 for one of them, and or actually no, it'd have to be closer to, it'd have to be a smaller probability. I don't know, like
When that
it's like just barely more likely. Like just barely more likely than all the other ones. Like let's say you have 5, it's like 0.21 and then a bunch of 0.19s. And then it would make a stick if you chose the highest probability one, when really their about balanced binary search tree would probably be best.
Good. Yeah. Good. Yeah. So what you say is like, okay, what is the probability? Instead of like being equal, it's like being equal plus epsilon, and next is like just perturb everything so that like they are basically almost the same, but the probability like a slant by a bit. And now you're gonna get like, if you just take the best, like the biggest probability guy, then you're gonna get like just a path instead of a balanced tree, and that's not good. Although like they all almost have the same probability. Okay, so but anyway, the point is like we need to choose a root somewhere, and so if we fix the root at R, we're gonna get these two subproblems, like everyone less than R and everyone more than R. And in this case, the cost that we're gonna pay is gonna be the cost of the best tree on the left and the cost of the best tree on the right plus 1, actually. Plus 1 because each key J here will pay probability Pj at this first step. You can think like that. Like every node will pay Pj here, and then you sum up over all pj on the root node.
You're gonna choose a stick like this.
And then just try all r.
If you bend it off.
Okay, take the best solution over all r. But then you need to recurse on the subtree, right? And in general, like the sub problem that you're gonna need to look at can be like the subtree that contains key from key I up to key j. And so what you need to do is just fix the root among this guy. And you look at a subproblem, start from on the left, like from key I up to less than r, and from to key j, and everyone that is more than r. And the cost that you pay is like the cost of base tree on the left and on the right. And then you pay this guy. What's this? It's just the total like probability mass from I to j. Like sum them up. Okay. And then you try for all r. Does this make sense that you need to add this guy?
Can you explain that a little bit more?
For sure. So, like, let's say that I have 3 guys, right? And this is P1, P2, P3. And now the expected cost here is maybe, I just gonna explain by example. Yeah. The expected cost here is like 2 times P1 plus P2 plus 2 times P3. These are just the depth of each node. But I can rewrite it in a different way. That is, I say that I can think like this one guy, I cannot pay P1 here and P1 here. So, and for P, like, so I can think like the first guy, I paid P1 once and P1 here. For the second guy, I paid P2 here. And for the third guy, I paid P3 and P3 here. So it means that I pay P1 plus P2 plus P3 here, and P1 and P3 here. So it's like the cost that I can have, that everyone pays to this is like the sum of all the P's here. And then I just recurse on this part.
Oh, sounds good now.
Yeah. So that's why like for if the subproblem is from key I up to key j, everyone need to pay at the root. Yeah. Okay. Make sense? So that is now our recursive formulation. Okay. Question about the recursion? Okay. How many subproblems are there in our recursion?
Isn't it just at most of n? Or am I?
Not quite.
So if each problem is 2 different subproblems on each level, then wouldn't it be like log n depth and 2 problems like 2 to the n for each of them?
2 to the n on each level? Not really. Like what I'm asking is like here is like we wanna find the best tree for like when the subproblem is start from I to J, and we might need to recurse from I to something, and from something to J. So, like, how many type of inputs can there be?
Is it n squared?
N square? Why is that?
It's sorted, so it's k, whatever. Sorry. And it would be the range between, like, it would be every pair would be like a range, and then that would be the subtree that you figure out the minimum cost for each time.
Good. So, yeah, like the type, like the input that is given to us is really just determined by I and J, right? Like we always get the interval of keys, start from key I, end at key J. So that's like the type of like the number of subproblems is just like for all I and J, that is at most like less at most n. So there are like an n square. So like the subproblem is like of this form. Yeah, just depends on I and J, and I and J is just two numbers such that is at most n, at least I. There are like n square many of this. Okay. So with this, you can expect that the running time is close to n square.
This is similar to matrix multiplication because in both problems we're like choosing where to split it and we're enumerating over that.
Yeah,
right?
yeah, it's really similar to like the recursion of when we do multiple matrix multiplication, because it's really a tree design, like the binary tree design problem.
Can you explain why it's n squared again?
Yeah, because like the input that you ever recurse to just gonna look like start from key I, end at key J. How many possible I can there be? Like I can range from 1 to n, J can range from 1 to n too. So that's like a n squared choices. Okay. So with this in mind, you can create like try to fill in the table. The table, well, like by the way, like once you kind of know how many possible subproblems can there be, you kind of see that okay, it just depends on I and J. Once you know this, then you know what the table should look like. Table should be indexed by I and J, right? So just create a table, the memo for IJ, such that it's like optimal arrangement when key start from I to J. Put the best case. The best case is when there are just one node, and the cost is like a PI. And now fill in the table in some bottom-up way. What's the correct bottom-up way? Well, like you need to like sort, like loop throughout this in such a way that the length of I and J is increasing. Like the length, like the size of interval is increasing. So like non-increasing order of I minus J. Okay. And then fill in the table using our recursion, which is like take the best root, right? And for each root, the cost is gonna be this guy, the total mass of the subtree, plus the expected, the optimal cost when you recurse on both sides. And take the best root, and then you get the solution for IJ. And at the end of the day, you return the optimal cost when you start with the first key until the last key end. Good. All right. The state of the art. So you see that the running time of this algorithm is n cubed because there are like a n squared loop here, and in each of these you spend O(n) time because you just take the best root. So that's like a n cubed time. Question about this? We are done with this. All right. Okay, so that's what we learned today. It's a really old algorithm, and it has been improved by a long time ago to n square. And now, if I ask you, is this the best? What's your guess? The answer is like I don't know. No one knows actually. People have tried hard to improve this. People have tried hard to do something like fine-grained complexity that I mentioned, like previous class. That like try to say that if you can improve upon this, then it would refute some conjecture. People try to do that too, and no one succeed in doing that. So this is like a really classical problem. Like just try to get the best binary search tree. Can you do better? No one knows yet. Right. Good. So that's a nice open problem. And good. So I actually have one more example, but I might not go through it because it's just another example. But I just want to mention that like it's just one of another classical problem that people look at for a long time. It's really nice application of dynamic programming. It's called RNA folding, and there are like some like you can have a look at the slides if you want, but wait, where is the but okay, there's a solution of n cubed, and then actually like alumni from this class 477 actually shows that no one can improve it to like show like that if you can improve it to be beyond n cubed, then it's gonna refute some conjecture. So he showed like that like okay, that's the best you can do. So just want to point out that this kind of classical problem like you can make progress on it. Yeah. Okay. Good. And so that's basically like I hope you see like really a lot of example of dynamic programming, like and Divide and Conquer last week. They have the same kind of theme, that is you have a problem, try to get a recursion, right? For Divide and Conquer, once you try to get recursion, you try not to make too many recursive call and try to minimize the problem size in the recursive call. For dynamic programming, you kind of don't do that. You just count how many possible subproblems you ever look at. Okay. And next week, we're gonna look at shortest path, which is still dynamic programming actually, but it's dynamic programming on graph. Like today we see dynamic programming on a tree, which is a special class of graph. Yeah, tomorrow, next week, it's just any graph. And you're gonna see how to solve shortest path. Okay, yeah, that's it for today.